Okay, this is your Math 2260 Chapter 6 review for Fall 2017. We're going to only go through 4 sections out of the chapter. So we're going to look at volumes using cross sections and the disc washer method, volumes using cylindrical shells, arc length, and areas of surface of revolution. So section 1 is volumes uses cross sections and the disc and washer method. So we're going to look at volumes with known cross sections first. So what this is going to be is a 3D shape, and if you slice it down in profile, you're going to see that the cross sections are known geometric shapes, so like squares, triangles, circles. And what we're going to do is the distance across the base of the region is going to correlate to some physical attribute of the shape. So it could be the diameter, it could be the base of a square, the diagonal of a square. We could even have the base of a triangle, the height of a triangle. So we want to make sure that we're paying attention when we're reading the problem and we're making sure we understand what attribute of the shape that we're going to be dealing with. If you integrate across the area of the cross section, you'll get the whole volume of a solid. So if you think about this with a really simple shape, right? So if we look at a cube, for example. Well, if you want to find the area of a cube, right, we know that, or the volume of a cube, excuse me, we know that the base, the width, and the height are all x, right? Because that's what a cube is. It's a square on all 6 sides. So what we want to do here, if you want to know the volume of a cube, right, one way of thinking about it is if you take the area of the base, which is x squared, and then you multiply it by its height, right, it does return x cubed. If you think about something like a cylinder, for example, the volume of a cylinder is the area of the base, which is a circle, pi r squared, times its height, which is h. So if we can find a formula as a function of x or y in terms of the area of either the base or one of the sides, and then we integrate across, it will in fact return the volume. So there's 2 ways to think about this. If the cross sections are perpendicular to the x-axis, we're going to write it as a function of x. If the cross sections are perpendicular to the y-axis, we write it as a function of y. So let's look at an example of what we're talking about here. So we want to find the volume of a solid given in the figure below, and it says the base of the solid is the region bounded by the function 1 minus 1/2 x squared. So, and then we also have the function g of x is negative 1 plus x over 2, and we want to also bound it by x equals 0. So if you look at the xy plane right here, right, this is sort of like an overhead shot, you can see g of x is drawn along here, right? And f of x is drawn along here, and x equals 0, right, is the y-axis. So the base of this guy, right, when we look at it in profile, are triangles. And then when it integrates up, right, the point of your triangle, right, makes a peak, and we get this kind of like prism sort of looking shape. So what you want to do when we're talking about our cross sections is we want to look at the base right here, okay? So when we look at it kind of in an overhead view, this is our top view. When we look at this, we see f of x is on top and g of x is on the bottom. So the distance across this region, which we're going to define as d, is actually going to be the distance from the function f of x to g of x. So you want to make sure when you're reading these, you're reading them from top down, because we want the distance to come out positive. If for some reason we were bound by functions in the y direction as a function of y, we would want to read from right to left, because you want to read from the positive side of the axis to the negative side of the axis, because we want to come out with a positive value. So what we've got here are triangles. These triangles here, if we look at the numbers we've got here, the base of this triangle is actually got a length of 2, right, because it goes from 1 to negative 1. And then we see the height of the triangle is also 2. What I don't know, however, is I need to figure out what D is across this region. So if we draw our triangle kind of straight up and down like this, this is actually an equilateral triangle. And what we have here is D, D, and then if I split this guy down the middle, we're going to call this D over 2. So I need to define the height of this triangle as a function of d. So then I can measure across my region. So we can use the Pythagorean theorem, right? Here's the height of our triangle. We can measure around and we can say, if I just look at one of the right side here and I use the Pythagorean theorem, it says that h squared, right, plus d over 2 squared is going to equal d squared. If we look at the entire triangle, if we wanted the area of the whole triangle, right, we could say, well, it's 1/2 base times height. The problem is I'm going to be taking many triangles all along here, and each one of their bases is going to be this distance d. So what I need to do is I need to solve this guy for d. So when we do this, right, the next line here, if I square d over 2 squared, I'm going to get d squared over 4, right, equals d squared. H squared, well, what I've got here is 1 minus 1/4, so that's actually 3/4 d squared. And if I take the square root of both sides, I can see that h is the square root of 3 over 2 times d. So the area of our triangles, and remember the cross sections here are the vertical sections like this, okay? So what this represents is the base of this triangle. So the area of our triangle is 1/2 base, which was d, times height. And so if I plug in my value for h, I'm going to get 1/4 d times the square root of 3 over 2d, and this works out to be the square root of 3 over 4 d squared. So if I can write an equation for d in terms of x, I can now define my area as a function of x. So we do that by looking across the region right here, and we see f of x is on top and g of x is on the bottom. So d is going to be the function f of x minus the function g of x. Now, one of the things that people get wrong in these problems is they don't distribute their negative signs properly. So what you want to do when you fill in the next line is you want to write your function of f of x, and then you want to subtract the entire function g of x. So you really need to make sure you use parentheses so you distribute your negative sign properly. So now what I have is 1 minus x over 2. The minus times a minus gives me plus 1. And then I have a negative x over 2. So if we simplify this, well, 1 plus 1 is 2. And negative 1/2 plus negative 1/2 is negative 1, so I have negative 1 times x. So d is 2 minus x. So now that I know what d is, I can now write my area as a function of x. So the area was the square root of 3 over 4 times d, which is 2 minus x quantity squared. So when I go to set up my volume integral, right, the volume integral as a function of x says, well, integrate the area function as a function of x with respect to x, and you need to make sure that the bounds on your integral are the bounds on x. So if we go back and look here, well, x can be 0 all the way up to 2. So my volume integral is going to be the integral from 0 to 2 of the square root of 3 over 4 times 2 minus x squared. So I can actually do this with a u substitution, right? I could FOIL this out and integrate everything with respect to x, but this is actually a really simple u substitution. So we want to make what's in our parentheses u. So let's let u be 2 minus x. And oops, I forgot the most important part of my integral. I forgot the dx. So make sure when you're setting up your integrals, this is absolutely necessary because this is telling you what variable to integrate with respect to. Because sometimes when you set up integrals, there may be more than one unknown quantity, and you want to make sure you're integrating with respect to the actual variable, and you would treat any other unknown quantities as constants. So if we let u be 2 minus x, then du is going to be negative dx. So remember, when you're doing u substitution, what you want to do after you write your du is you want to solve this for what you actually have in the integral. So I don't have the negative 1 up here, but I've got the dx. So that means when I go back to translate this into variable u, I'll replace dx with negative du. The other thing we want to make sure that we do is we want to make sure that we keep these bounds in the right variable. This is actually implied that this is x equals 0, x equals 2. So if you write your new integral with bounds from 0 to 2, but you changed a variable u, it's wrong, right? And so you might plug in the wrong values. So one of the things we can do, this is a pretty straightforward integral, is we can go ahead and change the bounds on u. If you change the bounds on u, then you don't have to do any more work when you're done with the problem. You never have to go back to variable x. So the way that we do that is we say, well, the first bound is x equals 0. So when x equals 0, you simply plug in 0 for x into this expression, and you'll see that u will come out to be 2. When x equals 2, u comes out to be 0. So now what I'm going to do is I'm going to translate this variable, this integral, to variable u. So I'm simply going to write the integral, right? Square root of 3 over 4 is just a constant. U represented everything inside the parentheses, so this just becomes u squared. And when I plug in my du, I'm really going to plug in negative du, so I'm just going to move the negative sign out front. My new bounds, and this is also important, if x equals 0 corresponded to u equals 2, 2 needs to go on the bottom. X equals 2 corresponded to u equals 0, so 0 has to go on the top. So you have to get the order correct. Now this is not typically the way we integrate, right? We want to go from the lower bound to the upper bound. And you are allowed to switch the order of integration if you multiply the integral by -1. So when I multiply by -1, it's going to make this negative sign go away. And so our new integral, and I'm going to pull the 3/4 or square root of 3 over 4 out front because we're allowed to pull constants out front. So now I have a positive square root of 3 over 4. The bounds are now 0 to 2, and I simply need to integrate u squared du. So integrating u squared gives me u cubed over 3, and I have to evaluate that from 0 to 2. So clearly if we plug in 0 here, we're just going to get 0. So really all I have to do is plug in 2. So I'll get the square root of 3 over 12, because I'm going to multiply the 4 and the 3 together, and 2 cubed is 8. So this is technically done, but I can reduce it just a little bit more since everything's divisible by 4. And so the simplified version of our answer is 2 root 3 over 3. All right, so let's look at a couple more of these with some different shapes. All right? So this one says, find the volume of the solids whose bases are bounded by the circle x squared plus y squared equals 4. So that is a circle with the center at the origin and a radius of 4. And we want to do it with the indicated cross sections taken perpendicular to the x-axis. So if we're going perpendicular to the x-axis, that means we're going to stay in variable x. So one thing that helps is let's draw our top view picture of this base. So for both of the shapes we're going to do, right, this is both of these have the same base, we can use the same kind of top view for both of these. So I'm just going to draw it right here in between. So what I have in the xy plane is a circle with radius 2 centered at the origin. So the distance across this guy, d, is going to be measured like this. And when you're solving a circle, right, if we want to look at this guy, if we want to plot it, the way you have to plot a circle is you would need to solve this expression for y squared. And when you solve this for y squared, you're going to get y squared equals 4 minus x squared, and then you have to take the square root of both sides. And the square root actually produces 2 answers for you. The positive case is the top half of the semicircle, and the negative case is the bottom half of the semicircle. So if you remember back in high school when you started plotting circles, right, you had to actually put 2 equations into a calculator or graphing utility to actually see the circle. So if I want to find D across this region right here, D, we read from top to bottom, D is going to actually be, I'm going to write it up here so we can see it, d is going to be f of x, right, which is the top function, 4 minus x squared under a square root, minus a negative square root of 4 minus x squared. So when you add these together, we actually get 2 root 4 minus x squared. And that should make sense, because if we look at the picture, if this distance from here to here is 4 minus x squared, and this distance is also 4 minus x squared under a square root, then it makes sense that we would get twice that when we measured across. So for the first problem, we have squares, okay? And so with a square, we know that the sides, all 4 sides are equal. So that means if the base is d that runs across the circle, the height of the square is also d, so the area of this is just d squared. But in order to integrate that, I need to write this area as a function of x. So a of x is just going to be d squared. Well, here's our d. So when I square this, the 2 squared is going to be 4. And then when we square the radical, it just returns the inside. So this is the function that I need to integrate. And if I look at my bounds, if we come back down here, right, this circle had a radius of 2. So that means the circle goes to negative 2 to positive 2. So my volume integral is negative 2 to 2 of 4 times 4 minus x squared dx. Now there's one more thing you can do. If you have symmetry, which we do here, right? So if I take the area, remember all the integral does is it's finding the area, right, on each side. Well, you can clearly see here the area to the right of the y-axis is going to equal the area to the left of the y-axis. So to make this a little bit easier on ourselves, we're allowed to say, well, this is the same thing as 2 times the integral from 0 to 2 of 4 times 4 minus x squared dx. And so it's going to be much easier to plug 0 into our final answer than it is to have to plug negative 2 and positive 2. So that's something you always want to check for when your bounds are going from negative a to a. Check to see if you have symmetry. And if the area on the left and the right are going to be the exact same, you can use this idea. And so we actually learned this back in the early days of learning how to integrate. So I'm going to take this 4 right here and pull it out front. So 2 times 4 is going to be 8. And when I anti-differentiate 4 minus x squared, I'm going to get 4x minus x cubed over 3. And now I just have to plug in 0 to 2. Once again, I'm going to scan this guy and I'm going to see, oh, well, every time I plug in a 0, I'm just going to get out 0. So I really only need to plug in 2. So this is going to give me 8 times, 4 times 2 is 8. 2 cubed is 8 over 3. And this simplifies into 8 times 16 over 3. For the next problem, we have the exact same base, so our d is still going to be 2 times the square root of 4 minus x squared. Okay, so because we're still measuring the distance across the region. But if we look at the cross-section of the shape, d across the region is actually the base of a semicircle. So we need to find out what the area of the semicircle is. So the base is actually represented by the diameter of the semicircle. So that's what d is measuring. It's the entire distance across. But the way we typically calculate the area of a circle is we'd say, well, it's pi r squared, where r is actually the radius. But if you have a semicircle, then you take pi r squared and you cut it in half because we only need half of the area of the circle. So if I want to write my radius, well, my radius is going to be d divided by 2, right? The diameter is twice the radius. So if I take my d expression here and I divide by 2, it just returns the radical itself. So this means my function as an area of x, or as a function of x, excuse me, is going to be pi over 2 times r squared. Well, when we square the radical, we just get back what's inside. So now that I have my function, or my area as a function of x, I can set up my volume integral. And once again, the bounds on x go from negative 2 to 2. So since I'm going from negative a to a, I want to look and see if I have symmetry, and I sure do. You can see that the y-axis just slices this guy in half. So if I take the area of the right side and double it, it's the same thing as getting the whole thing. So I can use my handy trick and say, well, this is 2 pi over 2 from 0 to 2 of 4 minus x squared dx. So when I go to integrate this, we can see these 2's cancel. So I'm just going to have pi times 4x minus x cubed over 3 from 0 to 2. So once again, I don't have to plug in 0 in this case. So I'm just going to have 8 minus 8/3. And this simplifies into 16 pi over 3. So even though we use the same function, the base of our solid was the same in both cases, we got completely different areas because the cross sections were different. And you can see from the pictures of the 3D shapes, we got very different shapes. And so this guy, you can see bevels as it goes up, because as the base of the squares get bigger, the height of the corresponding squares will also get bigger. So it rises up and then comes back down again, and we get these shapes on either side. For the semicircle, as the diameter gets bigger, right, this is the biggest the diameter will be is right here, you can see the curve of the circle, and so what you actually end up getting is half a sphere in this particular case. Right. So when we use the disk method is formed a little differently. So what we do is we take a region, we're going to have some kind of base, and then we're going to rotate it about either the axis itself or some line. And because we're doing a 360 rotation, all the cross sections will be circles, where the radius is measured from the axis of rotation to the outer edge of the region. So if we're rotating about a horizontal axis, the radius will be a function of x. If we're rotating about a vertical axis, the radius will be a function of y. And so if you look at here, we're still simply integrating the area across the region to get volume, but in this case, a of x is actually pi r of x squared, and if we have to write this as a function of y, it's pi r of y squared. So this is the same concept we did before, except we know all the cross sections are going to be circles. So that's why we have this nice easy formula to use. So let's look at an example of how to apply this. So we want to find the volume of a solid. That's found by revolving the region bounded by the graph square root of sine of x and the x-axis about the y-axis, and the bounds on x are going to go from 0 to pi. So if you actually graph, right, the square root of sine x from 0 to pi, this is what you get. So it's bounded here and it's bounded here. And just like before, if we're rotating about the x-axis itself, you measure the radius from the axis of rotation, right, up to the outer edge. When we spin this around, this is what the solid's going to look like. It kind of looks like an egg. So you can see the radius, right, is right here. So the radius, if you look at how the radius is drawn, it's going from the x-axis up to the original function, and that is the definition of the graph itself. So our radius here, r of x, is simply the square root of sine x. Then we need to square the radius because we're going to plug it into pi r squared, so the radius squared is just sine x. So the volume of this region will be pi times the integral from 0 to pi of sine of x dx. So the pi out front stays because it's just a constant, and the antiderivative of sine of x is negative cosine x. So I'm just going to move the negative sign out front, and now we need to evaluate this from 0 to pi. So we're going to have negative pi times cosine of pi, and cosine of pi is negative 1, minus cosine of 0, which is positive 1. So we'll have negative 1 minus 1. And so we're going to get negative pi times negative 2, which works out to be positive 2 pi. So that is the volume of that region. All right, let's look at another one. So this time we want to take the graph of 2 minus x squared and the graph of g equals 1, which that's just a horizontal line at 1, and we want to revolve it around the line y equals 1. So this time we're going to have to make a slight tweak when we look at the radius. Because if you look at the graph, the radius goes from here up to here. It doesn't start on the x-axis. So your radius cannot be the height of the function because that would be measuring it from all the way down here, and that's not what it is. When we rotate the solid around the line, you can see the radius is right here, right? Because it goes from the axis of rotation out. That's what a radius is. So what we have to do now is when we read this region down, right? Remember we read top to bottom, it's going to be f of x minus g of x. So the radius is the top function minus the bottom function. So the upper function is 2 minus x squared. The bottom function is 1. So we say 2 minus x squared minus 1. Well, 2 minus 1 is 1, so this just turns into 1 minus x squared. Then we need to square the radius. So when we square this, we can FOIL this out, and we can say 1 minus 2x squared plus x to the 4th. So be very careful because this is not 1 minus x to the 4th. You have to actually FOIL this out to get this expression. So now we need to look at the bounds on x. So x goes all the way from -1 to 1. So our volume integral is going to be pi times -1 to 1 of 1 minus 2x squared plus x to the 4th dx. Once again, I see I'm going from -a to a, so I want to check for symmetry. And sure enough, the volume of the right side is exactly equal to the volume of the left side. So I can change the bounds and say, well, this is 2 pi times the integral of 0 to 1 of 1 minus 2x squared plus x to the 4th dx. So now I'm ready to integrate. And the antiderivative of this is x minus 2x cubed over 3 plus x to the 5th over 5. And once again, I can see if I plug in 0, all of these terms become 0. So I really only have to plug in 1 here. And I'm going to get 1 minus 2/3 plus 1/5. If you're taking an exam, I would let you stop here. But if you actually want to get a common denominator, this works out to be 16 pi over 15. So notice when we did the disk method, we got solid circles, right? So one thing to keep in mind on both of these problems, if we go back and look, notice how the region and the axis, there was no gap, right? It was, you got a nice solid circle. So if I were to slice this guy, like if it almost looks like an egg slicer, you would see nice solid circles. Same thing's true here. There was no gap. There was a gap between the x-axis, but that's not what we rotated around. The region was nice and tight and flush up against the axis of rotation, so that's what guaranteed us we were going to get circular cross sections. Okay. The washer method is actually the same as the disk method with one slight little twist, okay? So I always say mind the gap, right? So a washer is something that a lot of people know from like putting you use a washer when you use a nut and a bolt, right? So a washer is a ring with a hole in it. So what's going to happen here is, what do we do when the region we're rotating, there's a gap between the region and the axis of rotation? Well, if there's a gap when you spin it around, that gap is going to create this inner hole, and the cross sections are actually going to look like this. They kind of look like donuts. So now what's going to happen is you're going to have two radii at play. You're going to have the radius of the inner circle, which we'll call little r, and then you're going to have the radius of the outer circle, which will be big R. So the way that you find the area of the cross sections now is you'll take the area of the big circle and you'll subtract the area of the little circle out of it. So that's why this looks almost exactly the same as the formula we did before, except you can see that reflected here. So be careful here. It's not big R minus little r and then we square it. We do pi r squared minus pi r squared. So we're going to have to make sure this is the outer circle, this is taking the inner circle. So you have to make sure you identify both radii when you're using the washer method. And I'll reiterate, when we look at the next example, you can tell which method to use because of the gap, right? So if there is no gap, little r is 0, and if you put 0, you're right back to disk method. So disk and washer are really just two sides of the same coin. So once again, if we're going around a horizontal axis, we keep everything in variable x. If we're going around the vertical axis, we keep everything in variable y. So let's look at an example. So we want to find the volume of the solid formed by revolving the region f of x equals square root of x and g of x equal x squared about the x-axis. So if you look at these two functions, right, we can see where they intersect. This is all we care about, is the region in between those two functions. And if we're rotating around the x-axis, well, there's little r, right? And there's big R. So we'll measure up to the upper function to get big R, and we'll measure up to the lower function to get little r. When we spin this around, you can see this little guy right here. There's the gap I'm talking about, right? We have a space between the axis of rotation and the region. So if you look at the 3D picture here, we actually have a hollow kind of like trumpet shape inside here. And so if we were to slice this guy down lengthwise, you would see that all of the cross sections are in fact washers. So little r of x, right, is measured up to the line y equals x squared. So that's just going to be x squared. And when we square that, it turns into x to the fourth. Big R of x is measured from the axis of rotation all the way up to the outer function, which was the square root of x. So when we square that, we're just going to get x. So when I set up my volume integral, I've got pi times the integral, and the bounds on x are from 0 to 1. So whatever variable you're integrating with respect to, that's the axis across you want to look. So you want the x coordinate here, and we want the x coordinate here. So this is going to be from 0 to 1 of big R squared, which was x, minus little r squared, which was x to the fourth, dx. So when we integrate this, we're going to get x times x squared over 2 minus x to the fifth over 5, and we'll evaluate it from 0 to 1. Once again, 0 is going to give me 0. That's not always true, but it just has been in these. And so I'm simply going to get pi times 1/2 minus 1/5, and this works out to be 3 pi over 10. All right, let's look at another one. This time, we're going to look at it with respect to the y-axis. So we're going to take this graph, which is x squared plus 1. It's a parabola that crosses at 1. And the line x equals 0, which is a vertical line right here at x equals 0. The line x equals 1, which was a vertical line at x equals 1. And the y-axis. So this is the region we have. But if we're spinning it about the y-axis, we have to measure the radii across this way. But look what's going to happen here. Everywhere above y equals 1, we get a washer, right? When you slice it across, we have this gap. Everywhere below x equals 1, we have a disk. We have no gap. So we're actually going to have to do two integrals in order to do this shape. And if you look at the 3D version of the shape, you can see you get a little bowl at the top, right? And then it's nice and solid everywhere below. So r of y, little r of y, is measured from the axis to the function itself. So r of y, this is the line x squared plus 1. So when we solve this for x, we actually get the square root of y minus 1. So technically, when you solve this for x, you get plus or minus the square root of y minus 1. We only want the positive case. That's this side. if we take the negative case, that's over here where x is negative, and we don't have to worry about that because when we spin it, it's going to give us everything we need. So when I square the inner radius, I just get back y minus 1. The outer radius is measured all the way out to the outer edge, and that's just a constant 1, right? So the function big R of y is just 1. So when we square 1, we just get back 1. So I'm actually going to call this region here region 1, and this region here region 2. So the volume of region 1 requires a washer method. So that's pi times the integral, and the bounds on region 1 are just 1 to 2. And it's big R squared, which is 1, minus little r squared, and that's y minus 1. Notice once again I had to use parentheses because I have to make sure I subtract the whole thing. So when you distribute the negative 1, what you're going to end up with is the integral from 1 to 2 of 2 minus y dy, because this ends up being 1 minus y plus 1. So when we integrate this, we're going to get 2y minus y squared over 2 from 1 to 2. So I'm going to have to plug in both values here. So when I plug in 2, I'm going to get 4 minus 4 over 2, which is 2, minus pi times, when I plug in 1, I'll get 2 minus 1/2. So I'm going to continue it over here. So that's pi times 2, which is 2 pi, minus 3/2 pi, and that works out to just be pi over 2. For the second region, I need to do a disk method. So the bounds for the second region, well, we just read everywhere below this line, so that's 0 to 1. And the radii is just one radius, and that's just the constant 1. It's 1 everywhere. So we're just going to integrate 1 with respect to y. So that's pi y from 0 to 1, and this works out to be pi. So the total volume of this object, right, is V1 plus V2, so pi over 2 plus pi, which is 3 pi over 2. Another way we can integrate volumes of solid is using something called the shell method. So with the shell method, what we're doing is it's kind of like doing like Russian nesting dolls, right? So if you know what those are, you open the doll's head and there's another doll smaller inside, and then you open that and there's another smaller doll and another smaller doll. So what we do this time, rather than, we're still going to rotate things around the axis, but rather than using the radius and doing a disc or washer, what we're going to do is, you can almost imagine like a cookie cutter, and we're going to hold the circle of the cookie cutter, right, parallel to the axis, and we're going to slice it and slice it and slice it. And what you're going to get are a bunch of cylinders. And if you take a cylinder, right, and you take a knife, right, and you slice it down the center and you unfold these. So these are hollow cylinders, or little tubes. And then inside of it, there'll be another one and another one, okay? So if we take these and we slice them and we just peel them off like layers, what you're going to get are rectangles, right? And if you want the area of this rectangle, well, the height of the cylinder is the height of the rectangle, but the length of the rectangle is actually the circumference of the circle created. And the circumference of a circle is 2 pi r. So we're still integrating area across a region, but what you'll see now is it's 2 pi, and this p is basically the radius, right? 2 pi p times the height. And so that's actually saying, let's take the area of each rectangle and then integrate it across the region. We can do the same thing in the x direction. However, notice what happens here. The variables switch. So if you're going around a horizontal axis for disc and washer, we used variable x. For shell, we use variable y. If we're going around a vertical axis of rotation, we go now to variable x. So in here, I've provided two diagrams so you can kind of see when you're going around a horizontal axis of rotation, the radius is still perpendicular to the axis, because that's the definition of a radius, right? Go from the axis out, but the heights run parallel. And so that's why when we're talking about a function, it becomes a function of y, because when we measure across this way, we're going to get a function of y. If you look at it around a vertical axis of rotation, the heights run parallel to the axis, and when we're measuring things this way, we use functions of x. And so you can see the radius here is measured from here out. So let's look at an example of how you would apply the shell method. All right, so what we have here is we have the graph of x minus x cubed and the x-axis, and we're only looking at it from 0 to 1. And we're going to revolve it about the y-axis. So there's a little gap here. If you tried to use the washer method to do this, you would have a problem. Because how do you define the inner radius versus the outer radius? Because it's all one solid line. So this is an example of a problem which you would have to use the shell method in order to find the volume of the solid. You wouldn't be able to do it using a disc or washer. So if we measure vertically up, right, to get the height, because the heights run parallel, we can see that the height is just going to be the function itself. And because we're going around the y-axis, we want to use variable x. So the height is just going to be the original function. The radius, however, is measured across, right, from the y-axis over. So that's just some value x, right? So that's how we measure x. You go from 0 to some unknown value x at that location, and then you plug that x into the function to get the height. So the radius as a function of x is just going to be x. So if we set up the volume of revolution, we're going to get 2 pi. The bounds on x are 0 to 1, and it's going to be x times x minus x cubed dx. I can distribute out the x to make it easier to integrate. So I need to integrate x squared minus x to the 4th dx. So this is going to work out to be 2 pi times x cubed over 3 minus x to the 5th over 5 from 0 to 1. And I only need to plug in 1. And so this works out to be 4 pi over 15. All right, let's look at an example of doing this when we want to rotate around the x-axis. So once again, right, the heights run parallel to the axis, so that means we're going to have to switch over to variable y, and the function is x equals e to the negative y squared. So the heights as a function of y are e to the negative y squared. The radius as a function of y is just going to be y, because I'm measuring from the x-axis up to that location, so that's just some random y, right, along that line, and then when I plug that value y into the function, it returns the height. So the volume is 2 pi. The bounds on y are 0 to 1. And we'll multiply these two things together. So we'll get y times e to the negative y squared. So in order to integrate this, I can do a u substitution. And when I do my u substitution, I want to let u be negative y squared. Du will be negative 2y dy. When I solve this for what I have, well, I've got the 2, I've got the y, and I've got the dy. I'm going to have to put in a negative du. I'm also going to go ahead and change my bounds so I don't have to go back to y. And I can say, well, when y equals 0, right, when we plug in 0 here, u equals 0. When y equals 1, u is going to be negative 1. So now when I translate this integral into variable u, remember we need the 2 for our du, so the 2 is going to disappear, right? We're going to have a negative pi because I'm going to have to plug in a negative du. The bounds are now going to be 0 to -1, right? Because just like we said before, you got to make sure you put them in the appropriate place. And the y got used with the dy for our du, and this just becomes the integral of e to the u du. Before I integrate, I want to switch these bounds around so they're in the right direction. So I can do that by multiplying by -1. Oops. And e to the u is really easy to integrate. We just get back e to the u. So I need to plug in the values from -1 to 1, or -1 to 0. So this isn't like the ones we did before. If you plug in 0 or -1 into this, you are not going to get 0. So we need to make sure we plug in both bounds. So we're going to have pi times e to the 0, which is 1, minus e to the -1. And e to the -1 is the same thing as saying 1 minus 1 over e. So this would be the volume of this solid. So what's the point of this, right? Why do we have the disc washer and the shell method? So one of the things that confuses students when you just see random integrals to solve is which method do I use, which one's the best, right? Some problems can be done using either method, and that's totally fine, right? In some cases, geometry is going to dictate which variable you use. So if we go back and look at this example, right, geometrically we said, well, we can't use the washer method because we can't distinguish between little r and r. There's no way to write this function where we can claim r and claim big R as a function of x, right? So we had to use variable y, right? In other problems, algebra is going to dictate what method we use. So if we come back here, if I wanted to try to use the disk method on this problem, I would have to solve this equation right here as a function of y. And when you solve this as a function of y, you would have gotten log of x. Well, we don't really know how to integrate log of x directly. So the algebra kind of dictated that it was going to be easier to work in variable y than it was in variable x. So the way that you relate these two concepts are right here. I made a table for you, okay? So you can see when you're going around a horizontal axis, disk washer lets you stay in x, whereas shell lets you switch to y. The vertical axis, disk washer requires y, but the shell method requires x. So one of the things you want to do when you're doing a problem is you want to think about, well, what variable am I stuck, do I have to be in, right? So sometimes geometrically, it dictates what variable you need to be in, and sometimes algebraically, it dictates what variable you need to be in. So pick your variable, then look at what type of axis you are, and this will tell you what method is required. So let's revisit this problem. We did it a minute ago, and when we used disk washer method, we had to split it up into two separate regions, right? But if we use the shell method to do this, we can do it all in one step. So using the shell method, we can see that we need to be in variable x, right? Because disk washer, we had to be in variable y. So if we can stay in variable x, well, the heights, right, which are parallel to the axis of rotation, are just the function itself. And the radius, when we measure across, is just going to be x, right? Because we said we're going off the y-axis, we go to some value x, you plug that value in, it gives you the height. So the volume integral is 2 pi. The bounds on x are 0 to 1, and I have x times x squared plus 1 dx. I'm going to distribute that x. And now I can integrate. So I really only have to plug in 1. And 1/4 plus a half is 3/4. So I get 2 pi times 3/4, but the 2's will cancel, and I get back 3 pi over 2. So if we look back to when we did this problem the last time, you can see when we split it up into two integrals, we got the exact same volume and the exact same shape that we did before. So this is an example of a problem where the shell method made it simpler to solve, but it was possible to do this both ways. It was just a little bit more complicated to use the disk and washer method. So let's look at another example where the shell method is absolutely necessary, okay? So what we have here is the graph x cubed plus x plus 1, y equals 1, x equals 1, and we want to rotate it about the line x equals 2. So if we wanted to attempt to do this using a disk or washer method, right, you can see we have this gap here between the axis of rotation and the region. So we would have to try to use washer. But washer says when you're going around a vertical line, you have to integrate with respect to y. But look at this function. I can't solve this for x, right? You can't really solve a cubic as a function of y. So I am stuck in variable x. So if we go back to the chart, right, it says, well, a vertical axis of rotation, if you have to use variable x, requires the shell method. So this is an example of the algebra got in our way. It wasn't really the geometry, we just couldn't do it algebraically. So if we want to use the shell method, notice here that the height is not measured down from the x-axis. So the heights are not the function itself. It's the function minus 1. We read it top to bottom. So you can think of this as it's really f of x minus g of x, because we only want to measure the height across the blue region. So the function f of x was x cubed plus x plus 1, and our function g of x was a horizontal line at 1. So this is going to be minus 1. So this just returns x cubed plus x. The radius also needs a special tweak. So because I'm measuring from here out, okay, the radius is going to go all the way to here. If I try to call this point right here x, well, x is the distance from the y-axis to there, but that's not what I want. I want the distance from this line to here. So remember I said earlier you want to read right to left. So this is the value x equals 2, and if we subtract off the value x here, we get the radius across. So we want that to be our radius. So the radius is actually 2 minus x. So what we're going to have is our volume integral is going to be 2 pi. The bounds on x are 0 to 1 because we only take the bounds where the region is shaded. And it's going to be x cubed plus x times 2 minus x. So I really need to FOIL this out to make it easier for me to integrate. And when we expand this, we get negative x to the 4th plus 2x cubed minus x squared plus 2x dx. So now I can integrate this, and I'll get negative x to the 5th over 5 plus 2x to the 4th over 4 minus x cubed over 3 plus 2x squared over 2, and I've only got to go from 0 to 1. So this is going to give me 2 pi times negative 1/5. 2 over 4 reduces to 1/2. Then I get minus 1/3. And then the 2's cancel, and I'll get plus 1. And so this works out to be 29 pi over 15. But once again, remember, on a test, you're not going to be allowed calculators, so I would let you stop here. And I actually would prefer that you stop here because I can easily see what you've done. It's just a lot easier for me to grade if you do it that way. So section 6.3 talks about arc length, right? And so arc length is simply when you have a curve, right? And we want to measure from point A to point B along the curve. So if you have like a flexible tape measure, you could do that, right? But what we want to be able to do is we can set up an integral and we can integrate the curve across this line and we can actually get the length of that curve. So you actually had a formula for arc length that you used back in like pre-calc, but that was talking about we were only looking at arc lengths on circles. So we were always measuring a sector of a circle. But now we can measure the length of any graph that we want. And there are three different forms of the arc length integral. If we have a function of x, we can integrate the square root of 1 plus f prime of x squared. If we're talking about a function of y, we can integrate 1 plus g prime of y squared. Or if the arc length is a parameterized curve, meaning that x and y are defined as some third variable like t or theta, we can actually set up this integral. All three of these things will provide the arc length of the line. It just depends on what the form of the original equation was. So why are there three different integrals? All right, so this is actually pretty neat. So if you want to know where this formula comes from, right, what we would do when we were first learning how to integrate is we would take the area under the curve and we would break it up into rectangles. And then we would independently calculate the area of each of the rectangles and then we would add them up. Well, we saw, depending on how we drew those rectangles, sometimes we got an overestimate, sometimes we got a slight underestimate, but by then taking the limit of that answer, when you guys did Riemann sums, we could turn it into an integral and we could get the exact area. So it's sort of a similar idea with arc length. So what you want to imagine is you grab a couple of points, right, on the arc length, and you actually draw secant lines. Okay, so we could say that this is L1, L2, L3, and L4. And if I could find the lengths of each of these lines, that's a pretty good estimate for the arc length. I've still got a gap here, so I'm not getting the exact arc length, but I could get pretty close. So let's just look at L1 for a second. And the way you would find the length of L1 is you would form a right triangle here, right? We would actually know these points. And we can say, well, this is the change in x for this triangle. This is the change in y. And if you wanted to get L1, and I'm going to draw it again down here for you. So for any arbitrary L, we could simply find L by looking at the Pythagorean theorem. So L, right, and this is also a variation on the distance formula. If you knew your two endpoints, right, the distance formula says you do x1 minus x2 squared plus y1 minus y2 squared, right, and then you take the square root. Well, if you look at this, x1 minus x2 is just the change in x, and y1 minus y2 is just the change in y. So I can actually rewrite this now as delta x squared plus delta y squared, right? So that means if I want the total arc length, I would take the sum, this should be like a curly guy right here, I would take the sum from 1 to n, because I would have n of these arc lengths, of all my various LIs. So if I replace LI with my radical, I would sum up delta x squared, right, and delta y squared for each one of my individual triangles. So if I wanted to write this as a function of x, right, I'm allowed to factor and delta x out of this. So if I actually factor delta x out, I'm going to get 1 plus delta y over delta x quantity squared times delta x squared. So if I were to distribute this back, you would see this cancels my delta x here, and 1 times delta x, I would end up right back here. So this is what I get if I do it this way, and I drop my sum. So then what we can say is, well, since this guy is squared, I'm actually allowed to take it out of the radical, because this is, excuse me, this times all of this, right? So then what I get is I from 1 to n of the square